Betelgeuse is a red giant star. If you put it where the Sun is, it would extend out to the orbit of Jupiter. Enormous, very unstable, and about to explode. These explosions are among the biggest bursts of radio energy in the entire universe, generating more energy than a billion suns. Are you prepared for what is about to happen? Betelgeuse, a massive red supergiant star and one of the closest stars to Earth, has recently undergone a remarkable dimming that has captured attention and mixed emotions globally. This dimming has led to speculation among astronomers and the public about its potential implications. Some scientists believe this unusual behavior could be a precursor to a supernova, a cataclysmic event that occurs when a star exhausts its nuclear fuel and collapses under its own weight, leading to a tremendous explosion. Such an event raises concerns not only among the scientific community, but also among the public as it poses questions about the potential impact on our own planet. Betelgeuse is a prominent figure in the constellation Orion, which is easily recognizable in the night sky due to its distinctive shape and bright stars. Also referred to as Alpha Orionis, it holds the title of the brightest and largest star in this constellation. Recent data collected by NASA's Hubble Space Telescope, along with observations from other observatories, have shown that Betelgeuse experienced a significant mass injection in 2009. This behavior is unprecedented for a star of its type and has piqued the interest of astronomers worldwide. While coronal mass ejections are a common occurrence in our own sun, the unique event observed in Betelgeuse adds an intriguing layer to our understanding of stellar life cycles and the dynamics of massive stars. The distance to Betelgeuse remains a topic of debate among astronomers. Some estimates suggest it is farther away, while others indicate it could be as close as 724 light-years from Earth. Accurately determining the distances of red supergiant stars like Betelgeuse is a complex challenge due to their immense distances and peculiar characteristics. Betelgeuse stands out as one of the brightest stars visible in our night sky, boasting a luminosity approximately 100,000 times greater than that of the Sun. However, this incredible brightness comes with a significant cost. Betelgeuse consumes its nuclear fuel at an accelerated rate, hastening the inevitable end of its stellar life. Eventually, the star will exhaust its fuel supply, leading to a dramatic disintegration under its own gravitational pull, potentially resulting in a supernova explosion that could give birth to a neutron star or even a black hole. Should our current astrophysical theories hold true, this raises an important question. Does Betelgeuse pose a threat to Earth? If a supernova were to occur just a few tens of light-years away from our planet, the consequences could be devastating. The explosion of a supernova can release an extraordinary amount of light, potentially rivaling that of an entire galaxy. Therefore, even if Betelgeuse is relatively distant, such as a star Alpha Centauri, the effects of its supernova could be profound and far-reaching. Remarkably, since the last supernova observed in our own galaxy in 1604, humanity has yet to witness such an event locally. However, a notable supernova did occur in 1987 in the Large Magellanic Cloud, located 169,000 light-years away. While that event had significant effects, it posed no direct threat to Earth, serving as a reminder of the scale and potential impact of such astronomical occurrences. The concept of a danger zone surrounding a typical supernova is intriguing and could have serious implications for life on Earth if a supernova were to occur nearby. Nevertheless, it's essential to understand that in the vast cosmic landscape, nearby supernovae are relatively small events when compared to gamma bursts, which are incomprehensibly more powerful and pose a different kind of threat. Supernovae can have devastating effects, capable of obliterating biospheres and inundating worlds with lethal radiation. For example, a particular type of supernova can lead to the destruction of a planet's ozone layer, leaving it vulnerable to the harsh radiation of the universe long after the explosion has occurred. This risk was highlighted in a recent study that introduced new potential dangers associated with massive stars that end their lives in a spectacular fashion. When giant stars explode in a supernova, they can reach some of the highest luminosities known in the universe. In fact, the brilliance of a single supernova can outshine the combined brightness of hundreds of billions of stars. This raises the question of what the implications would be if Betelgeuse were to undergo such an explosion. If a supernova were to occur, Betelgeuse would become the second brightest object in our sky after the Sun remarkably. Despite the distance separating it from us, Betelgeuse, which shines more brightly than a full moon, would become visible during daylight hours. The sheer intensity of the explosion would result in a display so dazzling that shadows would be cast even in complete darkness. Such a spectacle would be both inspiring and terrifying, demonstrating the raw power of cosmic events. While the visible light emitted by a supernova is indeed spectacular, it constitutes only a fraction of the total energy released during such an event. Although high levels of visible light can pose risks, such as temporary blindness, the greater concern lies in the high-energy radiation emitted alongside the visible light. This radiation typically manifests as X-rays and gamma rays, which can have far-reaching consequences. One of the most significant dangers posed by this high-energy radiation is its ability to catalyze the depletion of oxygen from the ozone layer that shields our planet from harmful solar radiation. Without a robust ozone layer, life on Earth's surface would be exposed to intense ultraviolet radiation from the sun, potentially leading to mass extinction events. In the immediate aftermath of a supernova, a variety of threats emerge over time. In the first moments following the explosion, the intense radiation released poses immediate risks. However, as time passes, cosmic rays, subatomic particles propelled to near light speeds, begin to infiltrate the solar system. These cosmic rays can further damage ozone layers and blanket the Earth's surface with deadly radiation, compounding the hazards posed by the initial explosion. Additionally, cosmic rays carry with them a significant portion of the total energy released by the supernova, and their long-term effects can linger for centuries. There is evidence suggesting that such events may have affected Earth in the past. For instance, elevated levels of iron-60, a radioactive isotope created in supernovae, have been discovered in fossils and lunar regolith. This finding indicates that Earth may have been impacted by supernova ejecta in relatively recent geological history, perhaps within the last few million years. Astronomers have previously concluded that there are currently no close supernova candidates that pose an immediate threat to life on Earth based on our understanding of the dangers associated with gamma rays and cosmic rays. However, ongoing research has uncovered additional potential risks associated with specific types of supernovae. These supernovae can emit long-range deadly radiation that poses a greater danger to planets like ours. The mechanism behind this involves a star nearing the end of its life being surrounded by a substantial disk of material. When the supernova occurs, a shock wave is generated, striking this disk and causing it to become extremely hot. As a result, the disk generates a considerable amount of high-energy X-ray radiation, which can travel vast distances through space. The most luminous X-ray supernovae have the potential to deplete a planet's ozone layer by as much as 50%, creating conditions that could trigger an extinction event within a staggering radius of around 150 light-years. Fortunately, as of now, no candidate X-ray supernovae have been identified in close proximity to Earth. However, this research has led to new insights regarding the galactic habitable zone, the region within galaxies where conditions are favorable for life. The findings suggest that this habitable zone may be subject to additional constraints. Specifically, the outer regions of a galaxy do not have sufficient star formation activity to produce the elements necessary for the formation of rocky planets. Meanwhile, the inner regions, where stars form and die at a rapid pace, pose their own dangers. Frequent supernova explosions in these areas can irradiate the surrounding space, increasing the risks for any potential life that might exist there. New research indicates that the inner boundary of the galactic habitable zone is likely located farther from the galactic core than previously thought, reshaping our understanding of where life could potentially thrive. So, what will the Betelgeuse supernova explosion look like from Earth? While it's reassuring that Earth's biosphere will likely remain unaffected, the spectacle itself will be impossible to ignore. According to experts, Betelgeuse will continue to shine brightly for more than 3 months following its explosion, reaching luminosity comparable to half that of the Moon, 9 times fainter than a full moon. In essence, it will manifest as a brilliant point in the sky, serving as a beacon that could be visible even during the day. Its striking brightness will captivate anyone who gazes upward, casting shadows in the night. This cosmic event will undoubtedly be a source of fascination for everyone on the planet. As the supernova remains visible to the naked eye for several years, its remnants will slowly fade. As scientists continue to study Betelgeuse, they are uncovering more about the life cycle of massive stars and the processes that lead to their explosive endings. Understanding these cosmic phenomena is crucial for gaining insights into the evolution of our galaxy and the formation of elements. During a supernova explosion, not only is light emitted, but a vast array of heavy elements like gold, silver, and uranium are forged in the intense heat and pressure of the explosion. This process is known as nucleosynthesis and plays a vital role in enriching the interstellar medium with the building blocks necessary for future star and planet formation. Interestingly, the remnants of a supernova, known as a supernova remnant, can become a stellar nursery where new stars are born from the dust and gas expelled during the explosion. This cyclical process highlights the interconnectedness of cosmic events and how the death of one star can lead to the birth of others. Researchers have identified various supernova remnants that are still forming new stars millions of years after the original explosion, showcasing the dynamic nature of the universe. Another fascinating aspect of studying supernovae is their role as cosmic distance indicators. Astronomers use Type I supernova explosions of white dwarf stars that reach a consistent peak brightness as standard candles for measuring distances in the universe. This method has significantly contributed to our understanding of cosmic expansion and the discovery of dark energy, a mysterious force driving the acceleration of the universe's expansion. Furthermore, the study of supernovae can offer insights into the potential habitability of exoplanets. Researchers are examining how the radiation emitted during these stellar explosions might affect planets orbiting nearby stars, potentially influencing their atmospheres and the viability of life. This research emphasizes the importance of understanding the environmental conditions that govern life across the cosmos. The possibility of observing a nearby supernova raises intriguing questions about cultural responses to such cosmic events. Throughout history, supernovae have inspired myths, legends, and artistic expressions. The explosion of a star is not just a scientific phenomenon. It becomes a powerful symbol in human culture, representing transformation, destruction, and rebirth. In many cultures, the appearance of bright new stars in the night sky has been interpreted as an omen or a message from the cosmos. Additionally, advances in technology have revolutionized our ability to detect and study supernovae. Space telescopes equipped with advanced sensors can capture detailed images and spectra of these events, revealing their composition and behavior. Ground-based observatories are also vital for monitoring transient events, allowing astronomers to respond quickly to observations and gather real-time data. The future of supernova research holds exciting possibilities. As new telescopes and instruments are developed, such as the James Webb Space Telescope, scientists will gain unprecedented insights into the life cycles of stars and the dynamics of their explosive deaths. These observations could lead to breakthroughs in our understanding of stellar evolution and the fundamental processes that shape our universe. In summary, the exploration of Betelgeuse and its impending supernova event serves as a gateway to broader discussions about stellar evolution, cosmic recycling, and the impact of these phenomena on life and culture. The study of such massive stars deepens our appreciation for the intricate and often violent processes that govern the cosmos, illuminating our place within this vast, ever-changing universe. Supernovae also play a crucial role in the cosmic timeline by marking the end of a star's life and the subsequent formation of diverse celestial structures. For instance, the remnants left behind can evolve into nebulae, which are vast clouds of gas and dust that serve as fertile grounds for new star formation. These regions can harbor complex chemistry, contributing to the emergence of organic molecules, the precursors to life. Moreover, the shock waves generated by supernova explosions can trigger star formation in nearby molecular clouds. This process, known as triggered star formation, showcases the interconnectedness of stellar phenomena and demonstrates how a single explosive event can initiate the birth of new stars and planetary systems. This highlights the significance of supernovae not just as endpoints, but as catalysts for future cosmic evolution. In the grand scheme of the universe, supernovae also contribute to the dispersal of heavy elements throughout the cosmos. As these elements spread across space, they enrich the material from which future stars and planets are formed, ultimately influencing the chemical diversity necessary for life. This cosmic recycling underscores the importance of understanding supernovae in the broader context of astrophysics and the origins of the elements that make up our own planet and, by extension, life itself.